Now with the correct title to the webinar on CLARA, an extended data record on cloud and radiation properties. And with this, I hand over to you, Karl-Göran.
Thank you. See if I can get things working. Right. Well, yeah, I'm Karl-Göran Karlsson from SMHI in Sweden, and I've actually been in the EUMETSAT project since the beginning. So I followed how the SAF has been evolving, and I will just repeat some of the things that Christine already have mentioned. Most important points on the EUMETSAT objectives. Our intention is to compile both global and regional scale climate data records, CDRs, as we used to call it, from various satellite sensors. And we also have a programmatic theme for the SAF, and that is to focus on components on the global energy and water cycle. And we, as Christina has said, we want to produce consistent CDRs with as long as possible temporal coverage. And we are talking about decades and not days or years, but decades in order to be able to say something on the climate and possible changes of the climate. And we also have this task to serve our users with providing data as quickly as possible. And there's a web user interface that people can order data from the EUMETSAT. So this is in short what we are doing. And then to go into this particular climate data record, this is based on a very old instrument, the advanced, very high resolution radiometer, which if considered today is not advanced and it's not very high resolution in comparison to what current sensors are. But the thing is, this is the longest available consistent observation data set from a multispectral imager. And here you can see some pictures from the launch of the first AVHR on Tyros N satellites in October 1978. And there is also an example of an image of a tropical cyclone Frederick from 1979. At this particular time, this was a sensation. I mean, it's the first time we could produce a multispectral image with this detail from a satellite sensor. And yeah, there's a list of the spectral channels. Normally, the aviation measures in 5 spectral channels. In the latest version of this sensor, it also a 6th channel was introduced. I don't go into details on exactly what these different channels do, but I will mention it for the clouds later here. But one should notice that this sensor was not at all intended to do climate studies. It was support to weather forecasting and some surface applications. So just underline that it was not intended for climate studies. It doesn't have the required accuracy that we require today from a sensor that should be used for climate monitoring. But the thing is, we don't have data from any other sensors for so long time. So it's still of interest for climate studies. So of course, there has been a lot of efforts to try to improve the quality and the suitability for climate monitoring applications. And I just show you one of those efforts, and that's for each AVHR sensor and each visible channel try to harmonize the data and take into account several things. First of all, a continuous degradation of the sensor, which means that the sensitivity decreases through the years, so which means that you have to multiply it with a higher and higher factor. In this case, you see a picture of the channel 1 slope, which is the factor that we multiply the counts recorded from the satellite sensor. That has to be try to compensate for this degradation over the years. And for that, for estimating this degradation, we compare with modern instruments like MODIS, and we compare against various targets on the ground, on the Earth's surface, which we consider are invariant, very stable. And we have something in the Libyan desert, we have something on the Antarctica, Dome Sea, and we also compare individual AVHs with each other to try to intercalibrate them, so we don't have these kind of jumps and things. So this is one major effort that has been done for the visible channels of the AVHR sensor. For the infrared channel, we have an onboard calibration system, so the situation is better in that respect. Yes. I don't have time to go into details of all the things we have done to prepare the, well, Christine mentioned that we have to use a fundamental climate data record. That means radiances that are intercalibrated and corrected in many ways. But we have done what we have, with what is possible, and together with EUMETSAT colleagues, there is now an AVHR FDR, fundamental data record, which can be accessed by everyone actually from EUMETSAT. And based on this quality controlled and corrected data sets, we have then produced the products of the CLARA data set. So the CLARA data set has an history, because we have had 2 previous editions of this data set. And you can see here what it really means, the acronym. It's the CMSAF Clouds, Albedo, and Radiation Dataset. And the -A in the name just is a notation that is based on AVHR data. And the first one was released in 2012, and then a second in 2017. And now in May this year, CLARA A3 was released. And there is a paper out, still in review, but there's a discussion paper available for everyone in the Earth System Science Dataset Journal. And the figures below in the bottom shows a comparison between CLARA A2 and CLARA A3 in terms of the coverage in time. And what you see here are the equator observation times, the local times when passing the equator in the morning and in the afternoon. And there is also observations in the evening and during night. So basically we have 4 observations per day, which we consist our data record on. And as you see, if you compare the two, we are now going back even to 1979 for CLARA A3. It's a new feature of the CLARA dataset, and it extends until 2020. And what is not shown here is that there is also an ICDR, as Christina mentioned, which continues after 2020. So the data record today is actually like 43 or 44 years rather than 42 as the original CDR. Yes. You can see that the observation times are not very stable, but I come back to that. And this is one of the problems with AVHR data. Well, here's just a very brief overview of all the products produced. We have a group of cloud products and a group of surface radiation products and surface albedo products and top of atmosphere radiation budget products. And I should say that the last one, top of atmosphere products, are completely new for CLARA A3 compared to the earlier data sets. And there's also an addition of surface albedo products introduced in CLARA A3. Before we only had one, and now we have actually 3 variants of surface albedo. So in the following, we will have a brief introduction to all these product groups. So I stop there now, and in case there are some questions, I can take them before going further.
Yeah, okay. Thank you so far, Karl-Göran. Rosa, are there any questions on Slido at the moment?
No, not at the moment.
Okay, so please, if you have any questions, don't be shy and type them into Slido. I think, Karl-Göran, then you can continue.
Yeah. Let me see. I think I've lost it here. Maybe. Here. Okay. I hope you see it now.
Yes, looking good.
I think I didn't start correctly. No. Yes, clouds. To do cloud product retrievals, you first need to identify what is clouds and not clouds in an image. And for that, what is good with the AVHR, which is a multispectral instrument, is that you have actually then a possibility to look at clouds in different spectral bands, which means that you can utilize some of the spectrally changing properties of clouds in terms of radiation. And to put it very short, in the visible channels, clouds are bright normally, daytime, and the surface generally dark, with the exception of snow. In the infrared channels, the thermal channels, clouds are generally colder than the surface. And then we have an intermediate channel, which is very interesting at 3.7 micrometer, where you can actually see some differences between water and ice clouds, and which also helps a lot in separating clouds from snow, which is otherwise very difficult from pure visible and pure infrared channel. So what we have actually done, we have learned these spectral cloud signatures. Yeah, I should also say that the images you see to the right, especially in the bottom right, these are multispectral images which are composed of 3 specific spectral channels of the AVHR, one which is more like a visible infrared image to the left, and one which is only based on infrared channels to the right. You can clearly see this is, yeah, you see perhaps that it is Northern Europe with Great Britain in the lower left corner and Scandinavia in the middle of this scene. That clouds look very different depending on the cloud type. So low clouds, yellow, and bluish is the high clouds, and in the infrared, you get even more impressions of differences between clouds. So these kind of differences what we use when we try to detect and characterize the clouds. And we have then matched our data with a reference data set from a LiDAR in space, where we have then learned these cloud signatures and composed a statistical classifier, which produces a cloud probability. And from this cloud probability, we can compute a cloud mask, which is easily, well, the easiest way is to just threshold it at 50% cloud probability, which is what we have done. And then count the number of cloudy and clear pixels in the grid resolution we are interested in. In this case, 0.25 degree grid resolution of the CMSOF datasets. Yes. And what had happened in CLARA A2? Yes, this statistical method is completely new. Before it was what is called, it was a thresholding scheme, which only produced a binary cloud mask. So nothing about the uncertainties of the cloud detection, which we now have at least the possibility to use in various applications. We have also upgraded input data quite a lot with, well, ERA 5. Reanalysis data is very important because for the infrared analysis, we use surface temperatures as a first guess from ERA 5, which is very important for the cloud detection at night. And there's also other things important. And overall, we can see that we have increased the global cloud amount by about 3%. Now, the estimation now is the global cloud amount is 66% averaged. And what these extra clouds have come from mainly over ocean surfaces, as you can see to the right, the difference between CLARA A3 and A2, but most of the new clouds also come from the Arctic region, Arctic Sea, or Arctic Ocean, where we in CLARA A2 had a very serious underestimation of cloudiness. So this is maybe the biggest change. Over land, not so much happens, but there are also cases where we overestimated clouds a lot in CLARA A2, some regions, in the Sahel regions, for example. So next product, cloud top height. How do you do that? Well, again, we use the multispectral capability of the aviation instrument. Especially, we look at two channels 4 and 5 at 11 and 12 micrometer, because we have what we call a different transmissivity in clouds and the atmosphere in these two channels. So if you compose a difference and map it against, for example, just the temperatures measured in 11 micrometer, you will get that kind of curve that you see in the plot. If you look at just not only at one pixel, but this pixel surrounding, you can imagine a cloud with a little bit different thickness. You get different values of this quantity, this temperature difference. And here we have composed a method based on machine learning, again using this reference LiDAR in space from this, which is called Calypso satellite, and learned how to use this information from the two channels together with some selected levels in the profile from ERA 5, this reanalysis data set. And based on these different inputs, it's like the pixel temperature and the coldest and the warmest temperature in a nearby surrounding. From that, we can make conclusions on the height of the cloud. And yeah, I've mentioned some things already. Machine learning based method, and this method also provides a rough error distribution, estimating the one standard deviation interval of the retrieval. And we have seen quite large improvements in the how to treat some clouds, especially clouds in the tropical region, the thin tropical cirrus clouds, where we now have increased the cloud top height with as much as 3 or even more kilometers compared to the CLARA A2, which seems much more realistic then. And we also had some problems with overestimation of some of the low-level clouds over ocean before, which has also been significantly reduced. You can see the difference plot to the rightmost plot here. And then we have, well, in the table I showed before, there were 3 what we call cloud physical products or microphysical property products. And that was cloud phase and liquid path and ice water path. These 3 are the kind of official products. But in addition, there are also other products which partly are needed for estimating the liquid water paths and ice water path. It's about cloud optical thickness, the effective radius of clouds for both water crystals and ice crystals. And in addition, there are also some completely new products about cloud droplet number concentration for liquid clouds, and also a cloud geometrical thickness product. When it comes to improvements from CLARA A2, it's mostly about better radiative transfer calculations and how to use ancillary data, for example, for surface albedo, which is important for very, very thin clouds, where you actually get the signal also from the surface. And better uncertainty estimates. And as I said, these additional parameters, CDNC and CGT. What should be kept in mind that these products are only retrieve data during daytime because we need these shortwave channels for retrieving those properties. And there are actually not only the channel 3B at 3.7 micron, there is for the last 10 years, we also have well, actually 20 years, there are also sensors which use the 3A channel at 1.6 micron during daytime. But for the long-term demand, that the default product over with all satellites involved, we have prioritized using the 3.7 micron channel. Some example, here's a comparison for the cloud phase product between CLARA A2 and CLARA A3, also compared with the 2 other datasets from ESA, CCI, and MODIS. And you see some changes. Overall, I can say it's rather stable over the year, with some exceptions in the beginning and in the middle of the time series. What is clear is that the CLARA A3, red or orange color here, is considerably lower for the liquid cloud fraction compared to CLARA A2. And this is related to the previous progress I mentioned about the cloud top height, because we have much more ice clouds now, because as a consequence of now having much higher cloud top heights for clouds. So there's kind of an interdependence between products here also to be noticed. And then one more example, liquid water paths, comparing with MODIS, CLARA A2, and ESA CCI. And you can see here that this negative difference values to all of the data sets, which again is very much related to the changes in high-level clouds, which has been a problem for most data sets, including MODIS and ESA CCI. So we believe, and with support from these cloud LiDAR measurements from space, that the CLARA A3 is closer to the truth here. I have only one more slide here now, and that's about something we call the joint cloud histogram. Because for some application, it could be of value to merge information from different cloud parameters. For example, you could want to know what is the frequency of high clouds at a certain level with a certain optical thickness. That tells you something about what clouds it is and the distribution, which is more compact compared to just looking at the cloud fraction and then cloud height. And then this joint treatment makes it easy to use to compare with, for example, climate model output. And here we have this, in this case, as I already mentioned, it's combining information from the cloud phase, well, water or ice, and the height of the cloud and the optical thickness of the cloud. And for doing this, we need to sample the data in a little bit higher, larger areas than the 0.25 degree resolution. So here we have everything collected in 1 degree grid. And the best use of these data is to accumulate them over selected regions. So then you get the kind of typical climatology for that region. And here you see an example where we have averaged all the accumulated results for the zonal band from 60 south to 60 north. So it's quite a big fraction of all of the globe for a rather long time period, 23 to 2020. And here you can see that the frequency of high-level clouds is quite high in relation to middle-level clouds, and also low-level clouds are more frequent. And you can see a little bit how the optical thickness also is varying in this area. We can clearly see a dominance of tropical high cirrus in this latitudinal band. Yeah, that's all I have on the cloud products.
Thank you very much, Karl-Göran. Can we have a look at the questions, Rosa, if there are any? Yes, there are a couple. First question is about the spatial resolution of the new data set. I'm sure you can say something about that.
Spatial resolution, I think I mentioned 0.25 degree in our monthly data set, or monthly mean data set, so level 3. But we also have what we call level 2B products, which is the original data, more or less in 5 kilometer resolution, resampled per satellite, day and night. So if you want more detailed information than in the monthly mean products, it is possible.
Okay, and where would people access these, the level 2B? Is that also via the CMSF web user interface?
It's yes, web
Okay.
user interface.
Okay, and we'll
I
hear
should
more
say
about...
that some of the products are actually also delivered to Copernicus climate data store. So it's not only from the web user interface you can get it, but some are available at other places also.
Okay, and we'll hear more about the web user interface later on from Steffen. And there is also the CMSF help desk, which is available via the webpage, and I'm sure the colleagues can help with dedicated questions. But here's another question for you. I'm not sure. Karl-Göran talks about Europe. Where are the pictures he talks about? There's, I don't know if everything went well here with the screen share. I don't know if you had, I don't know out of my head if you had any European images in your slides.
Well, I had, let me think now. I had an example over Northern Europe, Scandinavia. That's the only
Okay.
example I showed. But many of the other slides were global, I
We're
think.
global, yes, that's what I.
So
Okay, yes. So maybe this was just a screen share technical issue. So the European pictures were from Northern Europe, Scandinavia. So next question here is, which are the cloud parameters that were revised in the RTM calculations? Can you talk a little about it?
it's a difficult question because it's a long list of products which are all retrieved in quite different ways. So I'm not sure exactly what the question is about.
Well, I think maybe we can also discuss that offline. So Livia, who raised that question, you may be able to elaborate a bit more on your question in the Slido, and Karl-Göran can see that afterwards and can reach out to you if that would be fine.
I think the question needs to be more specific here.
Yeah, and I assume it may be also a bit of a longer answer and a longer discussion that may be needed. But Livia, you can also reach out to us after the course, and we'll put you in touch with Karl-Göran, and I'm sure Karl-Göran, you will be happy to discuss further.
Yeah.
All right, so far on the clouds. Now let's look at the radiation at the top of the atmosphere, and the expert on this parameter is Tom Akkermans. Tom, the floor is yours.
Thanks a lot. I'll try to share my screen here. Okay. See it?
Yes.
Hello. Okay. Great. So, good afternoon. I am Tom Akkermans from the RMI Belgium, and I will present you the top of atmosphere radiative flux products from CLARA A3. At the top of atmosphere, or TOA, we define the incoming solar radiation, which is then distributed over the various components of the Earth atmosphere system and returns to space as reflected solar flux or as outgoing long-wave radiation. The nature of these quantities, which are defined at the TOA, makes the use of satellite observations especially useful. The current state-of-the-art for TOA fluxes are the CIRRUS products. And CLARA A3 aims to provide some added value. First of all, by a prolongation back in time from 2000 to the late 70s. By increasing the spatial resolution from 1 degree to 0.25 degrees. And by offering synergy and compatibility with other CLARA A3 products, such as the Cloud Mask. Note that this is the first time that these variables are included in the CLARA portfolio, so it's not possible to compare our results with earlier versions like CLARA A2. So a simplified version of our processing chain is shown below. First, we start with two narrowband channels with either reflectance for RSF or brightness temperature for OLR. So RSF stands for reflected solar flux, OLR for outgoing long-wave radiation. First, a narrowband to broadband conversion is performed using empirical regressions. Then a directional to hemispherical conversion is performed using angular dependency models. And finally, an instantaneous to daily mean conversion is performed using temporal interpolation models. So here you can see an example of the daily mean RSF product for a certain day in June 2008. And to demonstrate the level of detail, we zoom in on an area and compare it with CIRRUS on the top panel. Okay. Here you see some examples of monthly mean RSF for several months in 2008. Now, this is a time series of deseasonalized global average RSF from multiple data records with CLARA A3 in orange. The effect of volcanic eruptions is clearly visible. And now this slide shows the same, but then for OLR. Finally, here are the long-term average TOA fluxes from CLARA A3, with the RSF on the left and OLR on the right. So now I'd like to show you some spatiotemporal insights in the data record. This is a Hofmüller diagram showing zonal averages versus time. Due to the large seasonality in the polar regions, we have to deseasonalize this graph. And this provides a much clearer view of the spatiotemporal RSF patterns. The same Hofmüller format can also be used to demonstrate the bias with respect to series data record. And this is shown here. The bias, which is pretty low in most latitudes and most years during this overlapping period, being 2000 to 2020. So now back to the CLARA A3 RSF. One of the prominent features is the intertropical convergence zone, which is on average positioned a bit north of the equator. You see this band here. However, some deviations from this pattern are worth highlighting. For instance, in the year 1991, with an apparent extension to the south here. And if you look closely, the entire year has somewhat higher values across all latitudes. Reason for this is the increased reflectivity due to the Pinatubo volcanic eruption. And this is shown on this slide here. The top panels show the daily mean RSF from CLARA A3. We see Typhoon Yunya approaching the Philippine Islands in the days leading up to the Pinatubo eruption, which happens on the 15th of June, 1991. So it's the fourth panel here. Subsequently, the volcanic ash clouds, together with the meteorological clouds, are dispersed towards mainland Southeast Asia. The bottom panels are the same sequence of daily mean RSF, but now from the ERA 5 reanalysis, demonstrating the large difference in detail and realism compared to CLARA A3. Now, the same sequence of days is shown here, but then for the long wave, for the OLR. But here we do have a good observation-based reference data record, namely the HERS OLR. And this is shown in the bottom panels with its own big disadvantage that, that it's a coarse resolution. Good. Two other deviations in this ITCZ patterns are visible in the years 1983 and 1998. And in these years, the ITCZ seems shifted a bit southwards from its average position. These periods, in fact, correspond with extreme El Nino events. So normally, during springtime, there are two distinct bands of the ITCZ over the Pacific, one north and one south of the equator. And this is what we see in the year 1982, the first panel here. So it's a monthly mean RSF for February. But during these extreme El Nino years, the two ITCZ bands, they merge together and the resulting band is shifted a bit south of the equator. And that's what you see in the next panel here in 1983. The year after, everything is back to normal again, and the two distinct bands are visible again in 1984. The same pattern shifting can be seen in the year 1998, again showing with its preceding and its subsequent year. Good. Now, something about trends. Here you can see the trends for the period 2000 to 2020. On the left side for RSF and on the right-hand side for OLR. The top panels are CLARA A3 and the bottom panels are the CIRRUS reference record. The units are watt per square meter per decade. The trends are very similar in most regions, except the RSF in the marine stratocumulus regions west of Africa and South America. Okay. Now here in this slide, I changed the reference for RSF in the lower left panel from Cirrus to ERA 5. And you can see immediately that it is not reliable in many regions, given the large discrepancies with respect to Cirrus. Now let's switch back and forth between the two. Go back, forward, back, forward. So you can see the difference with ERA 5. Going to the long-term trends between 1979 and 2020 in this slide here. For RSF on the left, we only have ERA 5 to compare with. But as already said, its regional trend patterns are highly doubtful. For OLR on the right, the trend map looks similar to the HERS OLR trends. Now we select some regions to show regional trends. We have 4 regions here. And voila, for each region, you can see a plot in which the black and blue dots represent the CLARA A3 RSF monthly means and trend lines. And the difference between the two is that the blue line is only calculated for the year, the period 2000 to 2020. So this is done to compare better with the Cirrus RSF, which is shown in purple. The light gray dots and line represent the ERA 5 RSF. And this slide here, the same is shown for OLR. And we have one more reference dataset, and that's the HERS OLR, which is shown in green. So that was it from my side. Thanks for your attention.
Good afternoon. This is Rob Rumeling. I took over the chairing the session from Christine, just to inform you. You can all hear me?
Yes, we can hear you, Rob.
Good. Thank you. That's good to know. It's always exciting to know if it's working. Thank you, Tom, for your presentation. Very interesting results. There is time for 1 or 2 questions on your presentation. Does anybody have questions at this point to Tom? So I don't see any, also not in Slido, if I'm correct. Good.
Yes,
then
sorry,
yeah?
Yes, there are no questions at the moment, as you can see, yes.
No, exactly. Then we move to the next presentation, which is from Jörg Trentmann, and it's on the surface radiation product that is also part of the CLARA data record. So Jörg, yeah, you can start your presentation if you want.
Okay, good afternoon. Can you see my presentation and hear me well?
Yes.
Yeah.
So, yeah, welcome everybody. So I will talk about the surface radiation data within the CMSAF CLARA A3 data record. So we just heard from Tom about the top of the atmosphere energy fluxes, so the downwelling solar radiation, the incoming energy from the sun, and the 2 upwelling fluxes in the shortwave and in the longwave radiation. And of course, the same fluxes we also do have at the surface. We have the downwelling shortwave radiation, the remaining energy that comes from the sun eventually reaches the surface. Part of it is already reflected by the surface albedo at the surface and going upwards again. However, in total, the solar part of the energy fluxes, of course, they warm the surface. So there's a positive flux from the sun to the surface. Looking at the looking at the long wave radiation, the thermal radiation, the net flux is negative. So this surface is losing energy by emitting long wave radiation from the surface, which is larger than the downward long wave radiation that reaches the surface. Overall, of course, the surface radiation budget in total is positive, so the surface gains energy from the radiation, and this again is compensated by the sensible heat flux, which results in the heating of the atmosphere, and the latent heat flux, which transport moisture into the atmosphere that eventually will end up as clouds and precipitation. So this is the overall concept of the surface radiation budget and the surface energy fluxes. The surface radiation fluxes are driven by atmospheric parameters, of course. So for the shortwave, the solar part, it's mainly driven by astronomy. So of course, during night, there's no radiation reaching the surface. On noon, there's a maximum radiation reaching the surface. So the second most important part is the cloud cover and their properties. And then we look at also at atmospheric constituents that impact the surface radiation, which is the water vapor, aerosol properties, as well as ozone. And of course, for the net radiation, for the radiation that's reflected again from the surface albedo, it's a highly relevant parameter. The good thing here is that all these parameters are either well known, like the solar zenith angle, or can be derived with good accuracy from satellite observations. In the long wave part, in the thermal spectra, the properties that drive the radiative fluxes are the low-level temperature and water vapor, as well as the cloud basite. These are responsible for the downward long wave radiation. By the land or the sea surface temperature, as well as the surface emissivity, they determine the long wave radiation that's emitted from the surface back into the atmosphere. And these properties are not well known. They're also very variable in space and time, and they cannot easily be derived from satellite observations with good accuracy. So for every satellite product, additional sources of information are required to get these parameters with a good accuracy. And I'll show you in a second how we do this within the CLARA data record. So this is just one slide, very quick overview on how the satellite retrieval of surface radiation works within CLARA 8.3. So here we're looking at the shortwave radiation fluxes, and we're looking at the surface incoming solar radiation, SIS, as well as the surface net solar radiation, SNS. These are the two parameters we are providing in CLARA 8.3. So the main part is to derive the surface incoming shortwave radiation. And the first thing is we're using the cloud mast that Karl-Göran already has described. That is new in CLARA 8.3, the CMA prop, probabilistic cloud mast. So if there's no cloud detected, we assume it is a clear sky pixel, and we more or less simply use the radiative transfer model to estimate the clear sky surface irradiance for this particular pixel. Of course, here we use additional information from ERA5, in this case, for water vapor, ozone, and other atmospheric constituents. If the cloud mass suggests that the pixel is not clear sky, but rather has some cloud contamination or cloud information in it, we use the reflected solar flux that Tom just talked about to relate this reflected solar flux to transmissivity and eventually to irradiance. So this essentially is the idea that if the reflective flux is high, there must be less radiation at the surface, like an energy conservation, basically. So of course, that is not so straightforward, because also the surface albedo plays a role and other components of the atmosphere. So there's quite a lookup table behind this relationship. These are the information we get from the satellite, but of course we also need to have additional information. I mentioned already the ERA5. Here now we also use the surface albedo, as well as our monthly climatological aerosol data to consider those impacts. From this instantaneous information of the all-sky irradiance, we of course want to derive the daily all-sky irradiance, which is eventually the official CNDAF product. And here we use the daily clear sky irradiance to constrain the daily all-sky irradiance that is shown in this formula here. So the clear sky irradiance, we can already, again, estimate quite accurately just from a radiative transfer model. And we weight this value with the ratio of the sum of the all-sky with the corresponding clear sky instantaneous irradiance derived. This is it's a quite smart way to get a good estimate of the all-sky daily mean irradiance, even if there are only very few instantaneous observations to consider the diurnal cycle of the solar radiation. From the daily SIS radiation, we calculate the monthly surface incoming solar radiation by averaging over the available daily means. The net shortwave radiation is estimated from the daily surface irradiance and the surface albedo that Akku will talk about in a second. And here we're using the pentat and daily data to eventually derive at the monthly net radiation. So this is the shortwave part, which is much more complex than the long wave part, which is, as I said, well, as I noted, we do it rather easily, I should say, in CLARA A3, since we mainly use the ERA 5 monthly surface long wave fluxes to estimate the long wave fluxes in CLARA. We do some rather simple correction with using the monthly cloud fraction from CLARA A3, just to ensure that it's not too inconsistent, I should say, between the long wave fluxes and the cloud coverage. But overall, the global mean and the temporal averages, they all remain constant, and they are driven by the ERA 5. We are providing the downwelling as well as the net long wave radiation, both as monthly means within CLARA. In the end, then we add the two monthly the two monthly net fluxes, the shortwave and the long wave fluxes, to come up with the overall surface radiation budget. So in the end, we have 5 parameters from the surface radiation budget. So this is just a climatological overview of all of those 5. With CLARA A3, for the first time, we can estimate actually WMO climate normals. So all these data here we're looking at is estimated as averages from 1991 to 2020. So that's also something very interesting, of course, for climate observations and for climate monitoring in particular. So on the left-hand side, see the shortwave incoming radiation, and the maximum radiation is in areas where there are low clouds, and of course towards the poles, there's less radiation also. The long wave downwelling radiation shows it's associated with the temperature of the atmosphere. So the higher the temperature, the more downward long wave radiation. The net radiation is shown here. So on the short wave, we see a similar picture than the incoming radiation as it should be. But then, of course, the surface albedo comes into play, that we have the desert areas where there's higher surface reflection and the net radiation is lower than in the neighboring oceanic regions where the surface albedo is much lower and the net radiation is higher. For the long wave, this value is negative throughout the globe. So there's in total an emission of long wave radiation, as I mentioned before, and this corresponds well to the length or sea surface temperature. So in areas with a high surface temperature, like the desert regions in Africa, Australia, and so on, you have a much higher emissions from the surface than downward radiation towards the surface. Overall, this then adds up in this number here, and this spatial distribution. There's always no net energy deposited in the desert regions from the radiation, but most of the energy is actually deposited over the oceans. So what's new in CLARA A3 compared to CLARA A2? And I mentioned already a couple of things. So first of all, we have new parameters. We now provide the net solar and long wave fluxes, as well as the surface radiation budget, so the overall net radiation. We think that these parameters are the most interested ones to our users for global energy studies. We do have improved satellite input data, and Karl-Göran showed this nice figure that in particular for the early years, we now have much better coverage from the satellite. We extended the temporal coverage, and also we have a better calibration now between the satellites. We use improved input parameters, in particular for the solar radiation, like the probabilistic cloud mass that was not available in CLARA A2, as well as the reflected solar flux that we now have available from the sophisticated retrieval by Tom and colleagues. Another feature that proved to be very positive was the use of the ERA5 surface albedo, where we use the climatological data in CLARA A2. So now we have a better handling of snow coverage on the surface that impacts our retrieval as well. So how does the data look like? So now we looked at the improvements in the retrieval, but why should you move onwards to CLARA A3 compared to CLARA A2? So first of all, we have a higher and improved quality of the data. So we're doing these validation reports, and we are comparing our data, in this case, the daily surface irradiance on the monthly surface long wave radiation, the downward long wave radiation. And these are just the numbers for the different editions of SARA from A1 to A3. And we're looking at the absolute bias here, for example. This has increased quite a bit since the previous editions in time. So the quality has increased. The same is true also for the absolute bias of the monthly surface downwelling. So the data is improving in quality and also in quality, but also in data coverage. So that's also one thing I would like to mention, that in CLARA A2 for the surface irradiance, we had some white spots. So we had some problems to derive the surface radiation in areas with high surface reflectivity. So these were kind of masked out as missing data. This has now been removed. This has been improved, also due to the use of the ERA5 surface albedo I mentioned previously. So now we are confident enough to deliver the data also on these areas, which are still demanding and challenging for the data retrieval, but we think that the data has a sufficient quality to be very useful to our users. We are now providing a CDR together with the ICDR. Sorry, we are running an ICDR and a CDR, and both, the combination of both now allows to generate global climate monitoring products. So this is just an example of the surface incoming radiation and the anomaly for last month, basically. So I think this is a very nice feature that that can be used now to detect and to monitor not really changes, but at least to look at how this certain month was different from the climatological average. So we have the reference period 91 to 2020, which is based on the CDR, and we have every month a new monthly estimate, and we can relate those to see that, for example, last month, apparently the Indian Ocean experienced much higher surface radiation than on average in the reference period. So talking about all these advantages, of course, there are also some known limitations and likely many unknown as well, but I can talk about the known radiation, the known limitations. So one thing to mention is that the solar radiation data are not complete in a spatial sense. So this is one example from the beginning of the data record, June 17th, 1980, surface radiation daily mean, and you can see the individual satellite orbits, and in parts of the globe we do not provide any data because there were too few observations. You can also see the area down here. This is where we know there's polar night, so basically we set this area to 0. But also in between you see some whitish regions where we have no coverage to the twilight. So this is just one satellite. Of course, as time goes by, we currently have more satellites in orbit, and this is the same day 40 years later. So from 2020, here we have 5 satellites that we use for the retrieval. So the global coverage is much improved. So there's now like missing data, like orbital missing data, but still we have this area here around the polar night where the sun is very low. We are in twilight conditions, and that is also very difficult for satellite data retrieval. So we basically stop the retrieval at at a certain stage, and this will also remain. This missing data will remain visible also in the monthly data. I mentioned before that the long-lived data depends heavily on ERA 5, so that is a little bit difficult if you want to compare it with reanalysis data and these things, so you should bear this in mind. I maybe briefly mentioned only that the aerosol optical depth that we are using is a climatological optical depth, so we are not taking into account the temporal variability of the aerosol, like the things that Tom just showed us on the Pinatubo eruptions. These are not explicitly accounted for in the retrieval. So, of course, one can calculate long-term trends, and we do this here. You can see it on the lower right. This is just a decadal trend of surface irradiance from the beginning of the time series to the end, and we see some reasonable values here. But of course, these should be evaluated if possible, or at least treated and interpreted with care, because the aerosol is not considered explicitly. Of course, we also look at these trends and compare those to observations, and this is from our validation report. So the trends do fit well to available BSRN stations in this case, but yeah, if you're looking in a certain area, you might want to check the reliability of these long-term trends, because the stability is always a tricky issue for all data records, of course. Recently, we noted that there was something happening with the calibration in about 2018. So we think that the trends after 2020 are not as reliable as before. Of course, we also suggest not to use the ICDR data to estimate any trends. That's one thing I should mention here, that the ICDR data is very good. It is very well suited to look at anomalies. But since the trends are very small, so here, for example, we're looking at like 2 to 4 watts per square meter per decade. So it's a very tiny change in the surface irradiance. So the calibration, of course, needs to be much more accurate to detect properly these trends compared to anomalies that are typically much larger than these numbers here. So that's it. So I hope I could convince you that we are providing the CLARA 3 high quality data of shortwave and long-wave radiation fluxes, as well as a radiation budget. The quality of the data, as well as its temporal and spatial availability, is much improved compared to previous editions. And I didn't show it here, but I would like to mention that it is competitive with other available data records from other satellites or also reanalysis data. The evaluated climate data and near real-time data, which is provided in very short timeliness, I think we are talking about 10 days here, does allow a very good, or is a good way to do climate monitoring. When analyzing the data, I mentioned that you should take care of missing data that is around in the data record, and that should be considered in particular when looking at spatial averages. And with this, thank you for your attention and look forward to any questions you might have.
Thank you very much, Jörg. Very nice to see how much you improved compared to A2. Also that now Greenland is part of the radiation project. Actually, it's a big achievement, not easy. Are there any questions on the presentation from Jörg? From people listening? I see things here in Slido. Oh no, sorry, I don't see anything there. You see, I don't see any hands either. Then I have a short question, just a short one. It's about the trend. So you say, because it's actually, so you say trends we cannot do from when we take the last 3 years on board, but anomalies are still trustworthy. But I can imagine that there's some region where the trend is very strong, where that still would be possible to look at the trends, or am I incorrect there?
No, of course, that is correct. So I just want to make this note of caution that, I mean, in general, I think it's true that for all measurement, basically, including satellite data, you need to be careful when looking at trends. And as I said, we know that there is some change in the calibration in the last years of the CLARA data record. So it's just an extra note of caution. I think the data can still be used till 2020. So for the CDR period, it's okay to do trends. But if you go beyond that, you want to take extra caution.
Yeah, I know. We had a discussion on that last week. With trends, you have to be careful, of course, because if the trend is not linear, how do you determine your start and end time for your trend calculation? You will find another trend.
Maybe I can comment on that also.
Yeah, for Klaus it's also important.
Yeah, we have unrealistic trends now in the ICDR because of a gradually decreasing quality of the calibration. And we hope to be able to make an upgrade of the calibration relatively soon, within months, I would say. And it's clear that this will generate the kind of jump in our results. So it's not just that you have a gradually decreasing quality of the calibration. We also try to improve it, but this can then generate these jumps, which are not then, again, artificial. These are artificial things. So the best thing is to be cautious with the ICDR dataset. And if it's very important that trends are okay, you should wait for the next reprocessing will be released in 2026, which we call CLARA A 3.5. Then we should have fixed this kind of gaps or jumps.
So this calibration issue already played also in the 91 till 2020 period, if I understand correctly.
Well,
I mean, do you only have to reprocess the ICDR, or do you have to do the whole thing new?
That depends. We noticed some weaknesses in the last few years after 2017. So I'm pretty sure that this will also be subject for reprocessing. And then we have seen problems in the very first years for Tyrosine satellite on the infrared channels. And if it is possible, we would like to revisit this and maybe improve it, but it's an open question still.
Yeah. Thanks, Jörg and Karl, for explaining that. So this calibration is a never-ending problem for all people who do climate data records. That's clear. But at least the trends that you have, so you are confident that the trends that you have over this 30-year period are at least meaningful and can be used. I think that's also a good message. So then I would like to move to the next presentation, which is from
Rob, there's one question on Slido. Should we go that?
Sorry. Well? Oh, yeah. Yeah, sure.
It's talking about the limitations of the AOD trends and whether AOD is used as input data set in the projects. And I can say that we do use the chronological AOD information. So every month we have a different, but every year for the same month we have the same AOD information. And we do use this data in the clear sky daily mean calculation. So I showed you the outline that how the surface irradiance is derived. And at this one point, we use the clear sky daily mean and weight this with the ratio of the all sky and clear sky instantaneous retrievals. Here is where we use the AOD information. However, there's no trend in this AOD information. So that's the only thing where we use the AOD as an input parameter. So that limits the AOD trends. We do, however, see that, as Tom has shown, that the RSF that we also use as input parameter already has a signal of the AOD trends, for example, for Pinatubo. So that we would have to investigate further how this RSF signal like the enhanced reflection in the RSF, that essentially should reduce, of course, the surface irradiance that we are deriving. Implicitly, we might actually do consider the strong aerosol events through use of the new RSF data record. But yeah,
RSF stands for?
Sorry, reflected solar fluxes.
Okay. Yeah.
That is what Tom and colleagues are deriving for the top of the atmosphere radiation, and that is input to our retrieval. So it's not yet quite clear how strongly the aerosol impact is actually included in our data record. So it's currently under investigation, but we do not implicitly take like a different data record and plug it into, like, for example, ERA does. Of course, they just read in some information on the aerosol and have a temporal evolution of the aerosol. And we do not do this because we do not have a good, at least not what we consider being a good data record of the AOD over time since the end of the 70s till now. It is hardly uncertain anyway. I mean, so we are still looking for a good reference data for AOD to be used in the future.
Okay, yeah, thank you, Jörg, for explaining that. So I don't see any other questions in Slido then, and also not in the chat. There are no questions. Good, then we go to Aku with the presentation on surface albedo.
All right, thank you, Rob. Let me also share my screen here. Just a moment. And hopefully now you will be able to see my slides. Is that correct?
Yeah, everything looks fine.
Very good. Let's go on. So now we come through the atmosphere, from the top of atmosphere level through the clouds, looking at the radiative fluxes, and we end up here at the surface level, looking at the surface description, which is the surface albedo component of CLARA. Surface albedo is a rather nice, intuitive climate variable in the sense that every one of us who has eyesight is continuously monitoring surface albedo through the good old Mark I eyeball. We are, of course, naturally quite adept at the qualitative level of albedo estimation. We all understand that fresh snow is pretty much the brightest surface you can find, which is much brighter than vegetated lands or asphalt or open water. But of course, we need quantitative estimates to do trend studies and to calculate the net radiative energy budget at surface or top of atmosphere. So we need to be able to also calculate the albedo from satellite observations. Now, one further note on the terminology here, which can sometimes be a bit confusing. So albedo really means the hemispherical reflectivity or reflectance. So the radiative flux, which is scattered from the surface to all directions. So we need to integrate to be able to estimate the total albedo. The satellites themselves do also observe reflectance, but they do so in one direction at a time. So a single satellite observation of the Earth's surface will only tell us about the reflectivity to a particular direction from a particular point on the Earth's surface. And we need then techniques to account for this bit of a discrepancy in our sampling, and I will briefly talk about them as we move along. Also, a good thing to note is that planetary albedo, of course, is a different thing from surface albedo. The planetary albedo that you calculate at the top of atmosphere level includes the effects of clouds and the atmosphere on the reflectivity, but those are both features that we try to get rid of when we are calculating surface albedo, which is just the reflectivity of the surface itself. Although there are some distinct flavors to that, and I will come back to those just now. So here, actually, I'm already showing you the data that we have. The animation that you see are the monthly mean blue sky surface albedos that we calculate for the CLARA data record running through the data. And as already noted, surface albedo can come in different flavors because it does not strictly only depend on the properties of the surface, but it also depends on the directionality of the incoming radiative flux. And here we generally follow the nomenclature of the MODIS data products that some of you may be familiar with, in that we generally speak of black sky, white sky, and blue sky albedos, and I'll briefly explain each of them. So if you were to stand on a planet without an atmosphere, all of the solar radiation would come from one single direction and then be scattered by the surface in the various directions. And the albedo that you would then measure from the surface would be the black sky albedo, quite naturally if you think of what the name really means. On the other side of the spectrum is the case where the incoming radiative flux is omnidirectional. It comes equally from all directions in the sky. In this case, the albedo that you would measure would be the white sky albedo, so radiation coming in from everywhere and being scattered variably into different directions. What we normally measure on the Earth's surface is something in between, depending on cloud cover, depending on the properties of the atmosphere. And this is then defined as the blue sky albedo, which is a weighed combination of the black and white sky albedos according to the sky conditions. So these are the three data products that we provide now in CLARA. We used to only have black sky albedo before, and the coverage is for all CLARA products from 1979 till 2020, and then continued with the ICDR products. A bit differently from some of the other products, we provide 5-day and monthly means, but not daily means, because we need more of an aggregation period to be able to get enough sampling to do a reasonable retrieval. And the spatial resolution is the quarter degree, as was asked before, and over the North and South polar regions, we also provide the data in equal area subsets at 25 kilometer spatial resolution, compliant with the EAST2 grid. And if you are familiar with the prior CLARA records, then I will say that our core algorithms are consistent with what was done before, but we now have improvements, for example, in cloud screening. As Karl-Göran mentioned, in CLARA A3, cloud detection is done on a probabilistic basis, which is good because it gives us the opportunity to decide on a threshold of cloud contamination possibility that we have to discard. Remember, we are looking at surface albedo, so all cloudy observations need to be discarded from our calculations lest they contaminate the estimates. The exact number at the cloud probability that we choose is a bit of an engineering trade-off, because if we were to say we want 90% probability of the scene being clear sky, this would mean that we get very few observations even during the course of a full month, which would lead to some problems in sampling in our albedo estimates. But if we relax the requirement too much, then we start to include cloud contamination. And for CLARA A3, we have arrived through testing at a fixed number of 20% cloud probability that we use to determine whether or not we should discard the observation or not. Also, as you see there in the animation, there is that appearing and disappearing no data region over the North Pole. There is the same kind of an inverted no data area over the South Pole, and this is of course the polar night. To calculate surface albedo, we need sufficient sunlight, and this is not doable over when the sun is too low or not available at all. So then these areas are marked as no data. We also cannot do retrievals if there are persistent clouds, and these lead to some other no data regions, particularly early in the record when we have only 1 or 2 satellites, and also if there is too high an aerosol loading in the atmosphere to enable us to do a proper correction for the atmospheric conditions. Okay, this I already talked about quite a lot. So it's both the surface properties and the atmospheric state which influence surface albedo. It is the surface material properties, in particular over sea ice and snow, which change the albedo that we can derive. For vegetation, it is also dependent on the 3D structure of surface, and we have models that try to account for this. But really, on a planet scale, the thing that most drives surface albedo variability is really whether or not there is snow or sea ice cover. And this is, of course, what you also saw in the animation that was running just on the previous slide. So, as noted, we don't do observations when we identify clouds or when there is insufficient solar illumination. We have to account for the fact that satellite observations take place only in one direction at a time. We have to know, or it is very advisable to know what type of land surface we are looking at so that we can try to account for the directionality in a reasonable way. And then, of course, the satellite only observes discrete bands of the shortwave solar spectrum. The albedo products that we derive and distribute are broadband, so covering the entire solar spectrum. So we need a method which is called the narrow to broadband conversion, which accounts for this lack of information in some parts of the solar spectrum. The algorithm itself is a bit complicated to go through, but I will just walk you through the main steps. So we screen for the clouds, we get rid of them, we screen for areas where sun is too low on the horizon. We also disregard observations that are too close to the AVHR swath, where the pixel size grows very large. We throw those out. Over mountainous regions, we attempt to correct for the topography effect for both the geolocation of the observations and in the observed reflectivity. And then the really important thing is the atmospheric correction, where we try to first strip away the atmosphere in order to derive the black sky albedo. Here we use ERA 5 data. As Jörg also noted, we need water vapor, we need ozone, we need the air mass. For aerosols, we actually use a self-derived observational data record from TOMS and OMI observations of aerosol index. It's a bit different from what Jörg was describing, because there are different sensitivities to aerosols between the incoming fluxes and surface albedo. So we have elected slightly different approaches here. But also for us, the last years of the CLARA record are treated with an annual climatology of AOD. Then we have some models that try to correct for the reflectance distribution in the different directions of reflection. And finally, for snow and ice, I will note that here we do something quite different, because we don't really have a universally valid scattering model which would work for both snow and sea ice conditions universally in all variable states of snow and sea ice. So what we really do is that we rely on the dense sampling of the AVHR to really gather, aggregate observations over most parts of the reflectance hemisphere, so that the average of those broadband reflectances provides a reasonable estimate for the snow and sea ice albedo, and our validation shows that this is the case. And then finally, the narrow to broadband conversion brings about the broadband albedo. This is just a very quick look at the A3 versus its predecessor A2 for the Arctic sea ice region poleward of 70 degrees latitude over the summer months where we have coverage. You will see that towards the end of the summer, July and August, A2 and A3 are very similar in the mean large-scale albedo that they derive. And this is, of course, what we hope for, not to change things too much. The early summer period shows a bit of a brightening in A3, which I personally find good. I felt that the A2 sea ice reflectivities in early summer were a little dim. So this is, in my view, a good step in the right direction, and most likely a result of improved cloud screening, as well as the update into the radiance intercalibration, on which all of the surface albedo is hugely dependent, of course, especially for all the trend calculations that you may attempt. This is just a very quick look at the decadal scale trends over the polar regions with the sea ice cover. So you will see as we go on, and this is relative to the 1980s, as we go on through the decades of CLARA coverage, you see, especially over the Arctic, the emerging intensifying losses in sea ice cover, particularly over Barents and Kara seas, but also in the Pacific sector and over Laptev Sea on the Russian side. So these are very consistent, of course, with what we've been seeing from microwave observations of sea ice, which is a good thing. Over the Antarctica, it's a bit of a more of a mixed bag of different trends over different areas, and I won't go into much detail on that side, apart to say that the large-scale trends seem reasonable and consistent. We, of course, do a very thorough, well, we try to do a very thorough investigation of the quality of our retrievals, so we compare against different types of in situ data sources. We have BSRN stations, which measure surface albedo at decadal scale. We have a few shipborne observations, drifting ice camps in the Arctic Ocean, which provide us with sea ice albedo, and we have a measurement network over the Greenland ice sheet, which provides us with more cryospheric coverage over the ice sheet and its margins, and the sites are shown here on this map. The data, it also shows the validation results on the top. I won't go into the details. You may see that the different curves track each other over the course of a melting season of the sea ice, and this is, of course, what we are hoping to achieve, so that we are able to track the emergence of the summer melt and its progress towards the end of the summer in late July and August. With the validation, there is one particular problem that I want to highlight. We are always required to provide our accuracy in terms of what is the estimated accuracy at the 0.25 degree or 25 kilometer scale. And this is, of course, challenging because the in situ measurements really measure just the spot on the ground. So there is a potential for very large discrepancies between what the in situ measurement shows and what the satellite estimates, simply because they look at different things. And we tried to quantify this with the use of high-resolution land cover data from Google Dynamic World dataset from Sentinel-2 observations, where we looked at the grid cells that contain BSRN sites, and we estimated the expected surface albedo based on land cover for these, and looked at how the bias that we see for these sites depends on the variability of land cover within these grid cells. And here you see a couple of examples of what the data look like over two sites in North America. Actually, one site in Estonia and one in North America. And it turns out, once you array our BSRN biases against the, let's say, homogeneity of land cover within the CLARA grid cell, it does turn out that low biases correspond to sites which are homogeneous in terms of land cover, whereas the higher biases typically are found in areas which are more heterogeneous. So this is the expected result, and I'm happy to say that this appears to be the case, which is shown here on the top right. The other figures just show biases over the entire data record on top left, and arrayed over our selection of BSRN sites and through the years of record. So for some sites, we've been able to do almost 25 years of validation without seeing very much systematic change in biases. So we can say that our stability appears to be rather good in terms of the radiometric stability, although some sites disagree more than others. Our predecessor data records have been quite useful, particularly for cryospheric applications. We hope that this will remain the case for A3. We do see relatively low mean biases against our reference observations with good stability, but we caution that this is by design. So we design for stability over large areas, over long time frames. If you pick a single grid cell and single year or a single month, you may see variability, of course, depending on how well we do for that particular month. So with the AVHR observations, you have to understand that scatter is always higher than for the more modern instruments like MODIS or VIIRS or even the Sentinels. There are a few technical artifacts. I won't go into much detail, so you may see a few ghost retrievals resulting from corrupted data that are hopefully easy to spot and get rid of. There is some indication that a few of the artifacts over Antarctic sea ice may be something that don't really conform to our expectations relative to CLARA A2, and we're looking more into this. I don't see a huge problem there, but it's possible that we may need to do more investigation on the Antarctic side. Over the Arctic side, I'm very confident that we are very consistent with also the predecessor records, which have shown their value in prior studies. And this pretty much just tells you what I just said. If you are looking at long-term trends, big areas, then this might just be the data set for you. We've had good use cases before, and we trust that the A3 will remain useful, particularly over the polar regions, but free to go with it also in the elsewhere, because it does have global coverage. And with that, I'm done. Thank you.
Thank you very much, Aku. Nice to see that this now is really a climate data record covering a 30-year period. That's very useful.
40.
Huh?
40 years.
Yeah, but at least a 30-year WMO period.
Yeah, yes.
That is, and it's even longer than that. Let me see if there is in Slido. There's another question. So I'm still wondering about the aerosol optical. The aerosols. So we had some volcanic eruption events during the last 40 years. So do you see that back in your time series, or does it march over these quite well? Because that actually kind of proves that you do the correction in a proper way. Do you see a fingerprint of these events in your data record?
For Mount Pinatubo, I can say that Mount Pinatubo does show a bit also in the surface albedo, because it led to a cooling which is seen over the polar regions. On the other hand, it also posed additional problems for us in terms of doing a proper atmospheric correction, because it changed the atmospheric composition so much over the course of 2 years. So it's a bit hard to say which of the changes are really fully there and which have contributions from the fact that we just cannot fully keep up with the changes that they which followed from the Pinatubo eruption. But certainly, I think the fingerprint is there.
Yeah, so also in the black sky albedo over the tropics, for example.
Yes.
Where it
probably
should basically not be visible, I would expect, like over the Amazon.
Probably not. So some of the features are then likely artifacts if you see them in the wrong places at the wrong time.
Yeah. Well, it's very difficult to remove, but it's that's a challenge. In the chat there is no questions, and I also don't see questions in Slido from anyone.
There is one question in Slido.
There is. Oh, okay, I don't see it.
Can you not see the share screen?
Maybe can you read it up? Or kindly provide some additional guide to new users on how to access the A3 CLARA surface radiation data? Is that the question? No.
Yes.
That's 20 minutes ago. I think this is a general question. So kindly provide some initial guide to new users on how to access the CLARA A3 surface radiation and cloud cover data for regional studies. That is a question.
I think that's a perfect transition for my part.
Yeah, because now we go to the... Yeah, that's a good point, Steffen. Because now we go to these kind of... So how to get the data and also how to use the toolboxes that are available. So if there's no questions to Aku at this point, then I would indeed say let's move to Steffen. And this question you can then... Maybe you first present and then you answer that question, or you present it you answer it during presenting.
Yep, okay. So after this nice presentation of the data, I will now show you how you can get access to the data and how you can work with the data. So the main access point is our web user interface, the wui.cmdaf.eu. And I will briefly go through the steps which I think are the most important while ordering our data. So the first one is you have to register once. That's mainly for statistic reason. Then you search your data. I show you how you can do this. And one important point when talking about climate data is the size of the data can get quite huge, and this really fast. So one important point when ordering the data is maybe to change the projection and to restrict the area you're looking for. That's a quite easy way to reduce the data size. I will show you this. Then you proceed to the time range selection. That's it. You put your data in your cart, log in, and click on place an order. Then you will get a confirmation email. And depending on how much is in the queue and how much has to be done with your data, you will get a download email, maybe a few minutes or at least a few hours later to download. And this process I will briefly show you now live on our website. The main entrance point to the web user interface is looking like this, wui.cmdaf.eu. And the first thing you want to do is to look for your data. The more details you know, the easier it is. I prefer the product search form. This is this one. So in our case, we are looking for CLARA A3. So we know the product family. You can click here on CLARA A3. Wait a little. And let's have a look. For example, we just heard about the surface albedo. Let's download some surface albedo data. You see here, there are different types of surface albedos in different projections and for different temporal resolutions. Let's look at the global monthly mean data, for example. On the next page, you get some details on the data, lots of references to manuals and validation reports and publications. And like I said, one important step is this point here, change projection, spatial resolution and domain to restrict the size of the data. Just for demonstration, let's choose a random little area here in Africa. For example, you can restrict, give detailed numbers here, or you can also use predefined regions from the Codex project. And you proceed to time range selection. So you see, you can get data from 1979 up to 2023. Let's make it a little shorter. For example, just for the WML reference period, for example, it would look like this. You click on Add to Order Card. Then you give your login details and place an order, and that's it. Shortly after this, you will get a confirmation email that you placed an order at our web user interface. And don't worry about the estimated size of the data. This size is basing on the original product without regional extractions. And a few minutes or latest a few hours later, you will get an email with a download link. And this link also includes the actual size of your data, so which is usually much lower than the estimation in the first confirmation email. So you click on this download link here, and what you get is a tar file. And I will show you in a few minutes how to work with this tar file. So summarizing, the web user interface is an easy selection online ordering tool. It's possible to get data on a regular basis. And there are some post-processing steps possible, like spatial and temporal selections. You get your data usually in netcdf format, which can be downloaded via this HTTPS download link. And of course, all data are for free. And if you have any question at any time, you can contact our user help desk, and you will get help quite fast. So now you have your tar file downloaded. Maybe you don't know what is a tar file. I expected a netcdf file, and you want to work now with the data. And what we provide is a quite simple software toolbox where you can start working with CMSAF climate data. And this one is called the CMSAF R toolbox. So like the name said, it's an R-based tool. But don't worry, you don't have to know any R or programming languages, because the toolbox comes with a nice graphical user interface. But if you want to, you can also use everything on the R command line. Everything is freely available via the CRAN repository of R. And the toolbox combines the most important steps to work with CMSAF data. The first step is the prepare data. So how can I get from a tar file to a ready-to-use netcdf file? The next thing, of course, is the most important one. How can I analyze and work with the data? And of course, in the end, you want to visualize your results, and that can also be done with the toolbox. So for this brief demonstration here, we prepared a few tasks which you can do. So we encourage everybody after this course to do this and to play a little bit with the data. Everything you need for this is you can download, of course, via the web user interface, or if you want to have just some example data, you can use this download link here, where everything from these examples can be downloaded. So let's have a look in some very simple tasks. So first of all, plot the long-term monthly mean of the CLARA surface albedo for August, first globally, and then a second for a country of your choice. Sounds not that difficult. So the only really R command you have to know is to the run toolbox command to start the toolbox. That's the main interface of the toolbox. You can see the three steps I just explained. The prepare step, this is the one to prepare a tar file. So you give a tar file, you can here have a look. You can choose a tar file, and this step is extracting all the data inside the tar file. Inside this tar file, you will find for each time step one single netcdf file. So for, let's say, daily climatology data, you will easily get thousands of files inside this tar file. And this operator helps you to extract everything. And after that, it merges everything in one ready-to-use netcdf file, which you can use for your analysis. I think due to time constraint, I will skip this part today, because in the end, you will get an ready-to-use netcdf file, which I already prepared, which you can download via this download link. And let's start. Here. Black Sky Albedo was the first. So this is what comes out of the toolbox as file, including the Black Sky Albedo for, in this case, globally from 1991 to 2020. And here is the main analysis interface of the toolbox. You can see you can choose the variable in this case. After using the prepare step, the file usually only contains one single variable in the end. You will see in the prepare step that the original file includes a lot of variables, especially for the surface albedo. To make it more to find easier the operator you're looking for, I introduced some operator groups. So our task now is to make a monthly climatology. for August. So we are looking for monthly statistics. Then we select our operator, which in this case is the multi-year monthly mean. And after this step, we want to select only the August, just for demonstration. So we want to apply another operator afterwards. So this usually takes a few seconds now. Now, from the 360 included time step in this netcdf file, the operator calculates 12 monthly means, including the time from 1991 to 2020 for each month. Let's wait some seconds. So here, this file you will find in the output folder of the toolbox, including the long-term monthly means. And now we want to select the selection, select list of months, and we want to have a look in the August, and we want to have a figure in the end. So we apply the operator. We have chosen, now you can see here, only data for August are included, and that's a quite strange color bar for albedo. So let's do something like this. And here you can see now the long-term mean for August from 1991 to 2020 for the black sky albedo of CLARA A1. That's our global picture. That's the first pass of the task. I saw we have a colleague from Brazil listening today. So maybe let's look how this data look for Brazil. We wait again a few seconds. And that's the mean of the black sky albedo for Brazil. So task 1 solved. Second task is plot a time series of monthly mean for cloud fraction for Nordschlepping and or a location of your choice, of course. We go back to our toolbox. Now we are choosing I prepared here the cloud fractional monthly means for Europe from 1997 to 2023. And what we want to do is extract the data for Nordschlepping. So the operator is called select data at a given point. I forgot Nordschlepping longitudes. 56, 16, and 6. That's correct. Yep. And what we get now is the time series extracted by a nearest neighbor approach for Nordschlepping from 1979 to 2023 August for cloud fraction. So that could be a nice starting point for your analysis. You can also do some simple things here straight in the toolbox. Maybe add a trend line. You can adjust the trend or the period you're looking for, or you click on Analyze Time Series and get some nice statistical plots, which you can also adjust like you want. Yeah, and that's task number 2 solved. That's how easy you can work with the EUMETSAT data. And the third task I will leave up to you. All data you need to solve this task, you will find under this download link. You know how to make a long-term monthly mean, and you will find the monthly mean for the August in this file, so you can easily do an anomaly. And if you do so, we would love if you could share your results via our Padlet page, which the link you can find here. So the installation of the toolbox, I can skip you, it's quite easy. You will find a lot of information material on our toolbox website. So there are manuals, YouTube videos, there's a paper, there's a Q&A document, cheat sheets. You will find some really nice tutorials also done by some trainees, which was really cool examples and a direct tutorial to reproduce it. And like I said, in the end, if you would like to share your results, we are happy to find these on our Padlet page. And with this, I give to Antonio, if there are no questions.
Yes, let me see. Are there questions? See some. You provided the links in the chat.
You will also get access to the presentation, so you will find everything. And also the presentation is recorded. In the end, you can have a look and play it a little slower if you want to. Yeah.
No, I think it's very relevant what you showed here, because getting the data is, of course, very important. Is there are there kind of trainings or help desks that people can?
Yes, of course.
Where they can go to with so when they want to get the data, because it's yeah. For some, there may be a learning curve there.
The EUMETSAT help desk, which you can write anytime. And there's also, like I said, a lot of already existing material on how to get access to the data and how to work with the data, which is linked on mainly on the Toolbox website.
Okay, and the links that you just discussed, they are all in your presentation, so yes. Which will be shared at the end of the of this session. Okay, thank you, Stefan, for that. And then we go to Antonio, which is, I think,
yes,
the last presentation of today.
Yes, the last one.
Yeah, it is. So it's on the Jupyter Notebook. So that is
Yes.
also on what can you do more with the data once you have them.
Yeah.
Or actually online it is probably. Well, you can explain.
Definitely. Yes. Yes. Okay. Just to, I am Antonio Vecoli, and I am supporting the climate application training service in EUMETSAT, and I'm here to show the users how they can replicate some of the, let's say, processing that Steffen has just shown, doing it with the Jupyter Notebooks, so coding in Python and not with R. And I started just with sharing a quick slide from myself, just to say that, sorry, can you see it again? Okay. So if the users want if we want to access the to work with the CMSAF data, with CLARA data, with the Jupyter Notebooks and Python, there are two main ways. The user can download the data from the link that is that has been already provided by Steffen, and they can download the data and work in the notebooks with the local machines of each own users. That is, let's say, the traditional approach. The new approach is trying to use data and notebooks on a virtual machine, so remotely on a virtual environment that is provided at this link that will be shown in the chat. And in this link, the user has just to register, and after the registration and an authentication request that will be received at the email, the user will be able to enter to a Jupyter environment where the notebooks are already pre-installed and the data are already accessible. So moving to the Jupyter Notebook. What I've prepared is a comprehensive Jupyter Notebook that, let's say, exploit not only the coding part, but also the possibility to explain what we are doing and to put also links to external resources. And here the notebook presents, first of all, the products that are used in the notebook, and for each product there is a link to the product in the CMSAF website, so to the web user interface. And this notebook then is structured into 3 parts. The first part aims to show to the users how it is possible to actually download the data in the Jupyter environment, and the data can be downloaded both from the public sources that is now available for the short course. So the users will find the NetCDS files in this link, and here it is explained how to actually download this data in the Jupyter environment without doing it locally. And this is the process to do it. And after the complete download, the data are available in the platform. Or the notebook also explains how to get the original product from the web user interface. So there is a short explanation that just replicates what Steffen has shown in the live demo for submitting an order and let's say receiving the email with the link to the product. And here it is explained how to download the data from the link that is provided in the email into the Jupyter environment, and how to enter the product that we obtain from the link, so that they will be ready to be processed in the notebook. So this is the first part. So how to get the data and to download the data from public sources and from the original CMSAF website. The second part begins to work with the data. There are 2 simple examples. One is how to read a single product, so a single NetCDF file that is in this case is a CIS monthly product for August 2023, and it is explained how to open actually the NetCDS file, what will be found inside, so the coordinates of the products, the variables that are inside the products, and how it is possible to extract both the timestamp, so to know actually which is the temporal step of the product, and the variable of interest. So in this case, we want to extract the CIS variable, and here it is the step to extract the CIS variable and to get the values of the variable. In the following step, it is explained how to visualize a single variable from a single product, and this is these are the, let's say, the lines of code, so the features that we can enable inside the Jupyter notebook to visualize the product with a proper color bar, with the grid lines, with the cost lines, and so on. The second part instead is aimed to show what the user should do in Python to work with the data record. So not with a NetCDF that only contains a single timestamp, but multiple timestamps in my time steps. In this case, we have a CFC product that goes from 1979 to 2023. So we have all the months that are included in this data record, and the notebook shows how it is possible to select a single temporal steps among the ones that are available in the data record, and of course how to select the variable and how to display the variable to visualize the value of the variables in a proper map. Then this notebook comes to the tasks that have been prepared, and they are similar to those that have been shown by Steffen in the R toolbox, but these are, let's say, implemented with the Python code. So the first one is to show the monthly mean of CLARA A3 surface albedo, black surface albedo, and I also added the monthly mean for the CLARA fractional cloud cover, and I put the expression of the fractional cloud cover before. So here is how to open the fractional cloud cover data record, how to extract the variable. Here, how to calculate the monthly mean for all the months from January to December. How to extract one of the months that we want to display, in this case, August. And here, how to visualize the long-term monthly mean of August with the period of reference, with the reference period that goes from 1991 to 2020. And at the same time, we have done it not only for the global coverage, that is the let's say the nominal coverage of the product, but we also extracted the product just for the area of Italy. So we have loaded the polygon as a shape file in the notebook, and this is the let's say the geometry of the polygon. Here we clip the data from the original CFC to the area that we are interested. And here we show how to visualize the data only for the region of interest. And then the same things have been done for the black surface albedo, obtaining the global monthly mean for August 2023. And the black surface albedo also only for on the area of Italy. Then we move to the second task, that was to extract a time series of monthly mean for the fractional cloud cover. And in this case, we have to fix, first of all, to determine, first of all, the location with the coordinates. We load the product as usual, and this operation is always the same. And we are getting the data in this moment from the public server that is being available for the courts. Here we obtain the full product. And here, with this operation, we extract the time series. So what we obtain is just a monodimensional array that cover 536 months. And then here are the instructions to actually visualize the time series over the location of interest. There is also the optional task that was the monthly anomaly of CLARA CIS for August 2023. In this case, here there is an empty space, and the user should try to, let's say, implement this task. There are the steps that are necessary to implement the tasks, and the user will also find in the repository, let's say, the solution of the task with all the steps that are necessary, but let's say explicated and explained on a different notebook, so the users can actually try to do it without any suggestion on the main notebook. And let's say this is all, and people are invited to register to the Jupyter platform and try the material that is already there.